All right, the last part of the notes is rice tables, which I've been telling you what were coming. And rice tables has nothing to do with rice. It has to do with the technique that we use to keep up with our information and solve for things. What it stands for is rice is reaction, so you'll write the reaction. The I is the initial concentration of the reaction. C is the change in concentration, so what kind of change is going to happen. And then E is what is the equilibrium concentration. So we're going to use this technique to solve for unknowns, whether that unknown is the concentration at equilibrium or use it to solve for the equilibrium expression. Okay? So the best way to do is just jump right in and get going. Okay? So for this particular reaction, 4NO is reacting and actually decomposing into O and O2. So first thing we do is we write the reaction. There is a mistake that we caught earlier. This should not be 4NO2 because there's no NO2 in the problem. So it should just be NO. So cross out that O2. It's just a typo. Okay? And we're going to go ahead and add our arrows in here because it is a reversible reaction, and that way in our rice table we can keep up with what's the product side and what's the reactant side. Okay? And then we look at the information that they gave us, and they tell us that we have 3 moles of NO are introduced into a 1 liter flask. When the system comes to equilibrium, we find that we have 1 mole of N2O. So it says determine the equilibrium concentrations of each substance and the Kc for their reaction. Okay? So the first thing we're going to do is figure out how we're going to put this in the table. For one thing, when we're talking about equilibrium concentrations, or equilibrium expressions, I just kind of gave you the answer. When we're talking about equilibrium expressions, what do we have to put in there to calculate that? Concentration, yeah. That was not, I gave you the answer, yeah. So 3 moles is not a concentration, is it?
No.
No. What is a concentration, though? Molarity, which is moles over liter. Our math becomes really easy when we have 1 liter. Okay? So in this case, our concentration is going to be 3 molar. Okay? And it is molar, but when we're putting it in our rice table, we're not necessarily going to keep the M in there because that makes the math complicated. I just want you to understand that you have to put a concentration in there. You can't just put moles. Okay? So I'm going to erase that M now so that you know that it's 3 molar. So I'm just going to say 3 molar up here so you understand that. Yeah. And it's just because when we start doing math, if we leave the M in there, we'll get a little confused and we'll think it's a part of the equation, and we don't want to do that. Okay? So initially, it says that it is introduced, and the only thing that's in there at the beginning is the NO. So this is going to be 0, and this is going to be 0 initially, because we haven't started forming that product yet. Okay? That is not always the case. Matter of fact, our next example is going to start out with products and reactants at the same time. That's totally allowed and doable. Okay, but in this one, it says it is introduced. That means there was nothing else in there, so it's 0. So then once this reaction proceeds, what's going to happen is the NO is going to start disappearing, correct? And what's going to start appearing? The products. So we don't know how much is going to appear or disappear, so we're going to call that change X. Okay, but we have to take care of the stoichiometry from the balanced equation. So NO is going to disappear 4 times the rate that oxygen would appear because of the balanced equation. So we're going to say that the change is going to be minus 4x. The N2O will appear 2x. It's going to appear twice as fast as the oxygen because of the stoichiometry in the balanced equation. So does everybody understand why I just use those numbers? If you are lost, dazed, and confused at this point in your life, ask me a question before I proceed. The main question is why is this side minus, why is this side plus? And to reiterate, because NO is disappearing, so we're going to take some away, and the products are appearing, so we're going to add some. Okay? So then at equilibrium, I like to draw this little line underneath so I can show that I'm going to basically add the two terms together. So at equilibrium, the NO is 3 minus 4x. This is plus 2x, and this is plus x. So those would be what the at equilibrium is. Now, luckily for us, they gave us some information in the problem that's going to help us determine what x is. And that is, at equilibrium, we found that there was 1 mole of the N2O. Again, we need to put that in molarity. The fact that we have a 1 liter flask makes life easier. So we see that 2x is equal to 1 molar. So what is x equal to? 0.5. We don't use fractions in here. Yeah. So since x is equal to 0.5, that means our oxygen is 0.5 molar, right? So we have one equilibrium concentration. We have a second one here that they gave us. So now we can figure out what the equilibrium concentration is of the NO. So we're going to say, so substitute 0.5 in there and do that math. So it's 1, because 4 times 0.5 is 2. 3 minus 2 is 1. So that becomes 1 molar. Okay? So now we have all of our equilibrium concentrations. Yay us. So now we can plug it into the equilibrium expression. Kc is going to be equal to products over reactants. So we're going to have concentration of N2O squared. O2. Sorry, I'm and then we're going to have NO to the 4th. This math is super easy because the things that we're having to raise to an exponent are 1s. So now plug in 1 squared 0.5 over 1 to the 4th. So we find that Kc is equal to 0.5. No units on big K, right? Yes, glad you agree. Okay? So, second follow-up question's not here, but I'm going to follow it up so I can get you thinking in these terms. With a K value of 0.5, would this equilibrium lie to the left or lie to the right? Left. It would favor the reactants, this particular, yeah. This one would favor the reactants. Okay? All right. Now, the next problem in the notes that I'm going to do is not in your notes. There was a mistake. So I want you on that side to don't cross out the whole page because we're going to do another problem instead. Cross out the problem and we're going to add in this other problem. Because the problem is I'm trying to keep these rice tables very simple. And in AP Chem, they're not always very simple and the math can become complicated. And so I'm so used to reading equilibrium problems for AP that I didn't think anything of that problem. It's like, oh yeah, we can do that. And I was like, oh, wait a minute. That one would require a quadratic equation, and we're not getting to that. We're doing baby rice tables, baby rice cereal tables, if you will, because that's some of the first solid food that babies eat. Okay? So, I'm going to pause the video and let you have a chance to write down the information that you're going to need for this next problem. So pause. Okay, so this one's going to work a little different because if you look at this problem, what's nice is everything is a 1-to-1 ratio in the balanced equation. That makes life easier. And it gives us the equilibrium constant this time. It tells us that our equilibrium constant at a given temperature is 5.10, which means where is this reaction going to lie? Left or right? Right. It's going to favor the products. Okay, so that's good to just kind of keep that in mind. And then it says 1 mole of each substance is present initially. That means we got all of them present initially in a 1 liter flask. Then it says calculate the equilibrium concentration of each species. So we're going to set up our rice table. We have 1 mole of everything in 1 liter. So what is our molarity of everything?
1 mole.
1. I made it easy for the notes. In the worksheet, it is not 1 liter flask. So you will have to figure out the concentration before you throw it in the rice table. Okay. All right, so I'm going to put a new slide up there because I can't fit what I need to do on this. I write too big, and it requires a little bit of work. So we're going to do a blank slide. So we're going to start with our rice table. We're going to start with the R, which is the reaction. So we're going to say CO plus H2O CO2. There are some textbooks and some teachers that call these ice tables instead of rice tables. They just leave out the R for the reaction, but you kind of can't do an ice table without the reaction, so be hard. So there's our R. Initially, we have, what did we say a while ago? What's the molarity of each one of those? 1. I'm going to do that as an I so we don't think it's 1 as well. So 1, 1, 1. Again, reminding ourselves that that means 1 molar there. Okay? The C is the change. So we're going to do minus X plus X on this side because our products will appear. And then I like to do the line for the E. And then, so at equilibrium, 1 minus X, 1 minus X, and then the products are 1 plus X. I'm still writing too big. Problem. Bam. So we have our equilibrium concentrations, we just still have X in there, but we could still make it work. So we said that the equilibrium is equal to concentration of CO2, concentration of H2 over concentration of CO. Nothing is raised. That makes life easier. So when I plug this in, it gave us in the problem that K was equal to 5.10 equals 1 plus X. Oh, looky there, it ends up being squared, right? 1 minus X squared. Well, that just got a little complicated, or did it? What can I do to simplify that? Huh? Did you say it? Oh, okay. I don't like you. It said, do you like us? Did you see that? I don't know where that came from. Cross out the squares? Yes, but how do I just cross out the squares? There you go. We are going to square root the entire thing. Because we can, and we shall. So now, the square root of 510 by 5.10 is 2.26. Take my word for it if you don't believe me. So 1 plus X over 1 minus X. So now we have to do what our little cross multiply, divide and conquer, collect your terms, all that jazz. Earlier today I just said, okay, that X is equal to this. And then some kids were like, what did you do? So we'll go over it in case you forgot. So I'm going to get rid of the denominator by cross multiplying. So I'm going to have 2.26 minus 2.26x equals 1 plus x. Now I want to put the same terms on the same side, and I want to try to keep things x positive when I can, right? So I'm going to say plus 2x on both sides. 2.26x, sorry. Then I'm going to do what? Minus 1, minus 1. So then I would have 1.26 is equal to 3.26x. Yes? Yes. Then x is equal to 1.26 divided by 3.26, which is 0.387. Is that my answer? No. No. Now we're going to take the x that we solved for and we're going to plug it in there, and there, and there, and there. So that when we do this, we're going to say that the concentration of CO is also going to be equal to the concentration of H2O, right? Yes. So 1 minus 0.387 is 0.613 molar. Yeah? Okay. And then let's do another color because it's so fun. The concentration of CO2 is equal to the concentration of H2. Now, the only reason we can do that is because they were all 1 to 1. If it was like a different thing, we couldn't just say they're equal to each other. It just so happens that 1, 1, and 1, everything's the same. So then, do I even need to write this down? It's 1.387. I don't think I need to do 1 plus that. I think you got that. Right? And that, my dears, is how that is done. The easy step. Baby rice tables. Right? All right. Any questions? If you are confused on any part of that, this would be a good time to ask the question.